In our previous video, we showed that geodesics are locally length minimizing by using the fact that radial geodesics are length minimizing. So let's show this. But before proceeding with that proof, we need to introduce a new concept. We need to talk about radial vector field. So recall that the exponential map gives a diffeomorphism from a neighborhood of the origin in a tangent space to M at P. So between that and a neighborhood of P in M. Thus, in particular, when we have an orthonormal basis for the tangent space, we can use this diffeomorphism to transfer it to get the so-called normal coordinate center at P. Let's say we identify the tangent space, right, with the tangent space of Rn, and write a normal basis this way, an orthogonal basis this way. And then we write the normal coordinate center at P this way, x1, xn. Then, generalizing the usual Euclidean distance function, we can define the radial distance function. We could also define the radial vector field. Remember here, this notation means we are summing over I. Okay, so let's see the intuition behind these concepts. Okay, so let's first look at what does it mean to say that the radial distance of x is less than some positive number epsilon. Now, in the Euclidean space, observe that r is just the distance to the origin. So to say that Rx is less than epsilon means that x lie inside the open ball of radius epsilon, centered at the origin. Now, how about on a normal coordinate chart in a general manifold? Remember, these notion, radial distance function, radial vector fields, are defined with respect to a choice of normal coordinate. So let's say we have a normal coordinate chart centered at a point P on a manifold. Now, what are the points on this manifold whose radial distance is less than epsilon? Well, remember, we got this normal coordinate by inheriting the coordinate from the tangent space. Remember that we had a diffeomorphism on a neighborhood of the origin, right? So if this radius epsilon is small enough so that the ball center at the origin with radius epsilon lies in that domain, then the point of the manifold with a radial distance as an epsilon are just a point lying in the image of that ball. So really this set of point is just a geodesic ball centered at P. Alright, so that's the radial distance. Now let's try to understand the radial vector field. Let's see what this vector field is in terms of coordinate. Let's look at the Euclidean space. Actually, let's even just look at the Euclidean plane R2. Now, we can think of tangent spaces to points in R2 as a copy of R2, right? So we can give coordinates to vector field. In that case, this vector field can be given by this coordinate. It will just be x over, so this r is square root of x squared plus y squared, right, comma y over square root of x squared plus y squared. So how does it look like? Well, at any point xy here, we have a vector pointing in the same direction, right, as the point xy, but of unit length. So we divide by this r here, so that this becomes unit length. So this is just a unit vector field, right, pointing out like this. Of course, there's nothing special about the Euclidean plane. We just mentioned that because it's easy to draw. In general, in the Euclidean space, this vector field is just a unit vector field given by at every point P, it's gonna point in the direction of the line through the origin, connecting the origin and the point P. And again, remember we divided by this r so that this is a unit vector field. Alright, now how about on a general manifold inside a normal coordinate neighborhood? Again, remember the normal coordinate here were inherited from the coordinate on the tangent space. So at any point Q here, this partial r, Q, would be the velocity vector of this radial geodesic, parameterized with unit speed. Observe in this picture, each of these radial geodesics correspond to each of these ray segments. And we can think of this vector as being the push forward of a radial velocity vector here. In particular, remember that its length, now observe that its magnitude is 1. Alright, so to recap, let's say we have a normal coordinate charge center at P, and from that we can define the radial distance function. Then the set of point x such that Rx is less than epsilon for epsilon small enough. That set of points is just a geodesic ball center at P. It's gonna be a diffeomorphic image of a ball center at the origin of radius epsilon in the Euclidean space. Now, for every point Q sufficiently close to P, the radial vector field evaluated at Q, so this radial vector at Q, it's a unit vector and it's going to be the velocity vector of this radial geodesic, so of the geodesic connecting P and Q but with your unit speed parametrization. Picture-wise, if this radial geodesic is the diffeomorphic image of this segment, right, then this unit vector, this radial vector, is just the push forward of this radial vector. Alright, so that's the definition of radial vector field and radial distance. Before moving on to show that geodesics are locally minimizing, we need one more ingredient. We'll talk about Gauss' lemma, which says that these radial vector fields are going to be orthogonal to the geodesic spheres.